Welcome to qnawire.
So in this problem, we have a police car that's catching a speeding car. So what that looks like is the police car here, and then the other car is coming, and it passes, and then after it passes, the police car accelerates from rest, and this is going at 130 kilometers an hour. So first, we just want to plot the position versus time. So we know that we're starting at the same point, right when the car passes. So that'll be at position 0. And then we know they also the police car catches up to it after 750 meters. So at 750, they're also going to be at the same point. And now first, the speeding car, well, it's going at a constant velocity. And what that looks like on a position versus time graph is linear. So that's the graph for the speeding car. And the police vehicle is starting from rest and it has to accelerate. So at first its velocity is going to be less than the speeding car, and then eventually it's going to be greater than in order for it to catch up. And when we have a constant acceleration plotted on a position versus time graph, that's going to look quadratic. So the police car has to start from here, slowly accelerate, and then catch up. Oh, that's not great. Here we go. And then it catches up with the car right there. And so if we were to extend this, this would look kind of quadratic like that. So this shows that they're starting at the same point here, and they're ending at the same point here. Now, to figure out the time it takes for this to happen, well, we know the velocity of this car, and I'm just going to convert that to meters per second. So we have 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. So this is going to be 36.11 meters per second. So now we have everything in the right units, and we know that delta x for this car, the speeding car, is going to be its velocity times time. We're going at a constant velocity. And the displacement we already are given in the problem is 750 meters. The velocity we also know is 36.11 meters per second. We have that multiplied by t. So t is going to be 750 over 36.11, which is 20.77 seconds about. The next part, we want to know the acceleration of the police car. And now that we know how long it took, well, it's going to take the same time for the police car. So we know t is 20.77. We know our initial velocity is 0 because we're starting at rest. And we're looking for the acceleration. And we also know our displacement is the same as well, 750 meters. And the obvious kinematic equation we want to use here uses all 4 of these variables. So delta x is v initial times time plus 1/2 a t squared. Delta x is still 750. V0 is 0. Well, we know the time, but this is just going to go to 0. And then we add in 1/2 a times 20.77 squared. And if you do a little arithmetic, you get a is, well, it's 3.477-ish, which is around to 3.5 meters per second squared. And finally, we want to know the police car's velocity once it catches up to this car, and the velocity of the police car here is going to be greater than the velocity of the speeding car, because it has to in order to catch up. So we can plug back into this. Actually, we don't want to use this equation because we want to find final velocity. So we don't know that. Now we know our acceleration is 3.477-ish meters per second squared. And so now we want to find velocity final, and the equation that uses that is going to be v final squared equals v initial squared plus 2a delta x. And again, we know our initial velocity is 0. That's going to make this pretty easy. 2 times 3.477-ish and 750. And from this, we get our final velocity rounded to 72.2 meters per second. And that's the velocity when the police car catches up to the speeding car.